Okay, welcome back to Engineering Geology and Soil Mechanics modules. So today we have come to another new topics, very important things in our geotech and soil mechanics field. It says seepage, which is the related to water flow into soils. So after this lecture, you may able to understand all aspects of the seepage related problems. First of all, you may understand the hydrostatic conditions. And then you also understand what is the Bernoulli equations, and then Darcy's law, and then flow nets. So far, you are unfamiliar with these all terminologies, but hopefully after this lecture, you are able to understand. So before we dive into details, we can think through the definitions of each terms. The soils are mostly permeable and porous materials. It is because the existence of interconnected void where water can flow through from point to point, from points of the high energy to a point of low energies. So water flow through soil is an important topic because it's necessary for estimating the amount of water flowing down to ground underground space under the different hydraulic conditions. It has something to do with the pumping of water for underground constructions. After some excavations, water probably comes in to the excavated area. We need to pump it out. How do we gauge the number of pump and then operation time? Let's say you can guess the amount of water you can plan to order your pump. And then also it has something to do with the stability analysis of your retaining systems and all dams that are subjected to seepage force. And then in order to quantify the amount of water we need, permeability, which is the flow velocity of water within the soils. Actually, the unit of the permeability of soil is identical to velocity. Meter per second? Yes. Centimeter per second? Millimeter per second? Yes. And then pore pressures is one of the key parameters governing the strength and stiffness of our soils. So we need to know the pore pressure under static condition or transient condition where the pore pressures and actually the pore water flow is occurring. This is known as seepage. This pore pressure, this is the water and flow through certain channels and then develop some pressures, which is the seepage pressures. And if the water is stationary, it causes some certain amount of pressures, which is the pore water pressures. This pore water pressures is measured relative to atmospheric pressures. So the levels which the pressure is atmospheric is defined as the groundwater tables. Later on, you can understand these two sentences more clearer by checking the typical examples. So below the groundwater tables, the soil assumed to be fully saturated. Yes, it is true. And when it comes to the no flow conditions, water just stationary, below the water tables. And the water may be static condition, right? And then the corresponding water pressure is called hydrostatic pressures that increases with water depths. You can imagine the swimming pool. On the other hand, when seepage occurred, the water pressure is not the hydrostatic condition anymore. Let's think about the hydrostatic pressure first. This hydrostatic water pressure or hydrostatic pressure can be expressed by unit weight of water, mostly 9.81 kilonewton per cubic meters, times water depth. This is static water pressure. So when you dive into the swimming pool, you may feel some pressure, right? 1 meter swimming pool, you can jump into the swimming pool and swim. You feel some pressures, which is the hydrostatic pressures. You jumped into bottom to, for example, 1 meters, and then our water unit weight is 9.81. So times 1 meter, the pressure would be 9.81 kilopascals, roughly 10 kilopascal pressures at the bottom of the swimming pool from the water surface, 1 meter surface. This is the hydrostatic pressures. This hydrostatic pressures gradually increases with depths. Yes, it is true. So when you install your standpipe piezometers here, you can, this kind of straw, you can install this standpipe, hollow pipe into the ground. We can read the water height, which is represented by HP. That is the height from the groundwater table to desired depths. This water pressure acts on at the bottom of our stem pipe, which is gamma W times water depth. This shape is always triangular. Here is the pore water pressure 0 because 9.81 times 0 meter and 1 meter 9.81 kilopascal, 2 meter 19 something kilopascal. Gradually increase. 2 meter swimming pool, you're supposed to feel more pressures. 3 meter, 4 meters. So how can we describe water flows? I do believe, as you already learned from the fluid mechanics or hydraulics modules, there are two states. One is the steady state. The other one is the non-steady state or transient. If water flow does not vary with time, it is the steady state conditions. On the other hand, if the water flow varies with time, we can call it the transient state. In this condition, water flow and seepage occurs. And then based on the fluid mechanics knowledges, water flow can be classified into the laminar and turbulent flow. But the velocity of seepage flow in most soils is too small. So the flow can be considered as a laminar flow state. It means the fluid flow in parallel layer without any mixings. It just water flow through the channel, which is the void. So as you can see, the standpipe, this is one of the piezometer, were installed here and there. And their readings like this. In the first figure, all standpipe shows the same water levels, horizontal levels, which shows the level of waters, right? In these conditions, there should be no water flow, just static conditions. Why these conditions, waters just remain constant? Later on, I can explain you in a theoretical manner. But right now, just intuitively, these conditions, the water, no flow, stationary conditions. In contrast, these figures, each standpipe shows the different horizontal levels, which means that water elevation are different and probably causes water flow from high to low in terms of energies. It is not a non-hydrostatic condition. Probably water flow through this way. So now it's time to take a closer look at the soils. On a microscopic scales, the water flow a very tortuous path between the soil particles, looking for the channels in the void space. But in a macroscopically, the flow path is kind of one-dimensional conditions. Let's say left to right, right? These each water individuals flow through this way, this way. It looks like very tortuous, but in a microscopically, the direction is just left to right. So the average discharge velocity, just V, can be obtained as the flow rate per unit areas, which is the Q. This is a flow rate in soils. A is the unit area of the soils, which is the normal to the flow directions. Actually, from here to here is the total A, and Q is the discharge rate. The unit is the cubic meter per second. And time divided by area, which is the velocity. Discharge velocity. This water flow is governed by the principle of Bernoulli equations, which is expressed by a head, like a pressure head, velocity head, elevation head. The terms head is used because the term this h in Bernoulli equation has the unit in length, meter, centimeter, millimeter. That's why we call it head. With respect to the differences in the length from a certain point to another point, water will flow from a point with a high value to the point with a low values. When you take a look at this, P is the pressures, kilonewton per meter square. rho g, which means rho is the density, g is the accelerations. And their unit is something like kilonewton per cubic meters. So cancel out. This unit is meter. The velocity square 2g. Also canceled out. This term also meter. Jet, this elevation from the datums. So it is also meter. That's why in the Bernoulli equations, the total head H is pressure head plus velocity head plus elevation head. This Bernoulli equation explains this phenomena, say the total energy of the fluid in motions, considering elevations and then pressures and then velocity. It is noted that the elevation head jet is the vertical distance of a given point above below a datum plane. Hi, Pro, how do you know the datum planes? You can decide. You can assume. This pressure head is the water height of the stem pipe, represented by the water pressures divided by unit weight of waters. This pressure head is the water pressures. How do you get the water pressures? Unit weight of water times water height. How do you get the water height? You can install your stem pipe. Then you can see the water height. This is the pour water pressures. High prof. We also have one more terms, velocity. When it comes to the water flow in soil, the velocity is too small as compared to water flow in the open channel and closed channels taught in your fluid and hydraulics modules. Because our water flow through the void, right? The velocity is too small, so we can't ignore the velocity terms. Goes to 0. So our total heads at any point of soil is pressure head plus elevation heads. Simple. Let's say we have 2 points in a soil. Water flow will flow from this point to this point. Why? This point has higher total head, and then flow through to these points with lower total head. Hi, Pro. How do you know this one is the has the high total head and low total head? How do you calculate? Simple. We can check water pressure plus elevation head. Let's take a look at this point A. How do we get total head at point A? Pressure head plus elevation head. Okay, elevation head is more intuitive. How do you get? We set a datum. Then check the distance. Oh, jet A. This is the elevation head. What is the pressure head, which is the pore water pressures? Gamma W times water depth. Gamma W is 9.81. Water depth, how do you guess? Just simply install your standpipe, your straw, and then check water height, which is the HP. Now it's expressed by the total head minus the elevation head. To make sure that our total head HA equals to elevation head jet A plus pressure head. That's all. This is fundamentals. Probably this point total head higher than this. Let's think through pool water pressures U at a certain point can be measured by a standpipe. The water level in the piezometer standpipe rises to a level of HP above the tip, such that water pressure at the toe of the standpipe is the same as the water pressure U in the soil surrounding the porous tip. So water pressure U can be calculated by water depth, HP times water unit weight. Let's think about two-dimensional water flow. We have inclined ground and installed the two different standpipes here and here, point A or point B, just the middle of the soil layers, right? And then the inclined soil body is a simplified our ground, simplified ground in Singapore, let's say. So as expected, there should be some differences between these two locations in terms of head. For examples, here's the datums. And the point A, elevation head, jet A. And this amount is the pressure head. So from here to here is the total head at point A. And about point B, our elevation head here, and water pressure is this amount. We have certain gap between these 2 points, which is the delta H. Delta H is head loss. So total head at point A equals total head at B plus delta H, right? Makes sense. And total head can be decomposed into pressure head, elevation head. Also, total head B also pressure head, elevation head, plus head loss. Now, we express our water flow in soil in a mathematical form. When you take a look at this equation, oh, water will flow from A to B. We have one more things I want to introduce you, which is the I. This is the hydraulic gradient, can be expressed in a non-dimensional form. Head loss along the certain lengths of the soil body. These two stem pipe install these 2 points, and their physical length is L. This head loss occurred while water flow through from here to here, length L. The ratio between head loss to water flow, water travel length is hydraulic gradient. Again, this hydraulic gradient is the head loss divided by flow length and flow distance. We discuss Bernoulli equations to explain why water flow in the soil. Higher total head, lower total head, water flow this. And then the differences of the total head is head loss. And then we know about the length of water flow and the ratio of the total head loss over our water flow length is hydraulic gradient. No unit, non-dimensional form. Okay, let's think about a slope like this. And then we also install two stem pipe. And then the total head, point A and B, is totally different. And then the differences is the total head loss. And then we also knows about the length. Yes. This mathematical background explain why water flow. So I'm gonna concrete your understand by using certain examples. So let's calculate the pressure head at point A or for the pressures. Oh, how do you know the for the pressures? Oh, it means that water unit weight times water depth. Okay, water unit weight is 9.81. What is the water head, water depth? We install stem pipe. Okay, thank you. This example already installed the water stem pipe and then clearly see 5 meters. That's all. Plus elevation head. Now it's 4 meters. Above the datums, it means the positive. So total head at point A is 5 plus 4, 9. Technically, 5 meter plus 4 meter. So 9 meter. So here, total head is the elevation of the water level in the stem pipe above the datums plus, and then, yes, above the datums. Yeah, it is true. Simply, Hi, Prof. I remember that you mentioned to me we can assume our data on our own. Yes, you can move here, here. What about this condition? Our data was relocated here. Recalculate the total head at point A. Total head equals to pressure head plus elevation head. Pressure head, which is the water height, water depth, still 5 meters. But datums different. Below the datums, which means that the elevation head -5. So +5 for water pressure head plus -5 meter for elevation head. Total head is 0. The location of the datum definitely affect our total head because elevation heads can be changed. But it has no effect on the pressure head because pressure head is just water height in the standpipe. Hi, Pro, what if we can't install the standpipe? No, we have to install to know pressure head. No other alternatives to check water pressure heads. Of course, we can install certain pressure sensors at a certain point, then you can guess. For examples, you can directly install your pressure sensors, and then that pressures tells you about 30 kilopascal. It means that your water height would be 3 meters because 30 equals to 9.81 times your water depth, roughly 3 meters. We can guess our pressure head from this way, but normally we install the standpipe. We install 2 standpipe. And as you can see, groundwater is the horizontals. Let's calculate total heads at point A and B. Just reminds of the how to calculate the total head. Total head is pressure head plus elevation head. Okay, elevation head, ZA, ZB. Pressure head, water height. Okay, thank you. This question also on behalf of ourselves already installed. This amount and this amount. Even if they have different elevation head and different pressure head, their total head are same. Total head looks same as each other's. In such case, water would not flow. Yeah, because there's no head loss. Head loss 0 divided by this length, always 0. So when is water stationary? Now you can explain, right? Total head. Our total head everywhere is the same and leading to hydrostatic conditions. These hydrostatic conditions causes hydrostatic pressures like a swimming pool. It looks shaped as a triangle shaped. When water is in motions, water flow is the transient conditions. There should be differences in the total head within these two soils. And there should be water flow, it is seepage conditions. Mm. 1856, Professor Darcy proposed a simple testing setup to check discharge amount of water or discharge velocity through the saturated soil, which is the one-dimensional flow conditions. Then we can control delta H, which is the head rules. And then we can also control the length. Then also he placed sand materials in between two different points. Probably that this sand material has a different total heads here and here. Because we can consider these 2 points, we set up our datum is here, right? Datum is same, point A and point B, but your water standpipe height. This point A, your standpipe is here because this point connected this water height and exposed to atmospheric pressures. Can you remember? Pore water pressure can be measured relative to atmospheric pressures. This point A connected to and exposed to air through this channel. So from here to here is the pore pressure head. What about the point, let's say B? These points exposed to air through this channel. Through this channel, no, we have sand. Through this channel. So point B, their pressure head would be the height from here to here. This Q, discharge rate, is the volume of water collected here per unit of time. So the unit is cubic meter, which is the volume per second. Based on the discharge rate, small q, we can calculate average discharge velocity divided by the cross-sectional area of the soil perpendicular to the flow directions. So this discharge velocity V is the discharge rate, small q, divided by area, large A. Through these testings, it was found that higher delta H, higher head loss we get the faster discharge velocity. And then longer travel distance, like L, we got slower discharge velocity. Intuitively, it makes sense, right? Okay. I probe. What is the Bernoulli? What is the Darcy's law? I'm got confused. I still don't understand. Don't worry. Every student doesn't understand at the first time. The Bernoulli equation gives us total head, elevation head plus pressure head. And then that's why probably water flow from A to B, because A is the total head is greater than B. And then Darcy's use the difference in hydraulic head to determine flow velocity, something like that. We focus on these channels. Since the velocity in soil is small, the Bernoulli reduced the pressure head plus elevation head, and Darcy's law then quantifies flow caused by these head differences. So in other words, this Bernoulli explains why water flow, and Darcy tell me about how fast it flows in soil. Okay? Again, Bernoulli equations explain me why water flow from to here to here. Why? Different to the red. The difference is head rules. So water flow this way. And then we can take a close look at this water channel. Darcy's law tell us about how fast water flows in soil. So based on Darcy's one-dimensional flow test, the discharge velocity of water through saturated soil can be expressed as V equals to Q divided by A equals to Ki. K is the coefficient of permeability. I is hydraulic gradient. Q, small q, flow rate, small q equals to Kia. Again, Q is Kia. K is the permeability, I is the hydraulic gradient, A is cross-sectional area perpendicular to the flow. Previously, I mentioned to you better to remember this equation. What is this? SE equals to WGS. SE, WGS. S, degree of saturation, E, void ratio equals to WGS. W is the water content, GS is specific gravity, relative weights compared to water. SE equals to WGS. I'll give you one more equations suggesting memorize. Q equals to Kia. Small q, flow rates equals to Kia. K is the permeability, I is the hydraulic gradient, total head differences, divided by water flow length and times A, cross-sectional area. Hi, Prof. How to memorize? Have you heard about Korean car maker? It is the Kia. Kia spells K-I-A. It's just for your informations. You are able to easily memorize this. Q equals to Kia, K-I-A. In the Darcy's experiments, we are adjusting the soil water flow lengths and then head loss. The average discharge velocity, the V, is derived from the flow rate small q using the total cross-sectional area. That's why Q equals to KIA. This Ki is the velocity V. But in reality, water only flow through the voids between soil particles. Technically, water flow through void. So the seepage velocity, the V prime, can be expressed in terms of the cross-section area of void. Q divided by AV. The quantity of the water flowing through the soil, the Q, always same. VA KIA equals to V prime AV. Water flow through the entire soils. Water flow only through the voids. The quantity of the water, amount of water are exactly same each other, right? So V prime seepage velocity equals to discharge velocity 1 over porosity. Porosity, what is the porosity? Indicator for checking void space. Of course, the void ratio also meaning the same, but in this case, A over AV. The porosity is VV over V. And then it is also same as considering AV over A, which is the porosity. And then the inverse relations is here. That's why Cp's velocity equals to just discharge velocity times 1 over N porosity. Discharge velocity is similar to Cp's velocity, but technically different. Now it's time to discuss about coefficient of permeability. This permeability is generally expressed in centimeter per second, meter per second in SI units, and strongly depends on the several factors like fluid viscosity, pore size distribution, void ratio, and porosity, and roughness of your mineral particles. It is rounded or it is very sharp, and also degree of saturation. In clay layers, in clay soils, the structures, right? The gibbsite, there is the stack, the shape. You remember, right? This structure plays an important role in permeabilities. And coarse material like sand and gravels have a relatively higher permeabilities. And then on the other hand, the fine materials like silt and clay has a low permeability compared to the coarse grain materials. The smaller one is of roughly 10 to the power of -8, -9. Water cannot flow too slow. It takes forever, 1 year, 2 years. And 10 to the power of -2, you can pour in water, quickly has gone. Water has gone. So mathematical formation of the permeability is expressed in terms of unit weight of waters and the absolute permeability and both viscosity of the water. And then this permeability depends on the temperatures, and then this temperature also affect the viscosity of waters. But we test soil's permeability in room temperatures, right? We are not supposed to do that permeability test in a very cold condition, in a very hot condition. It's just room temperature in the lab. That's why our permeability has the consistent values. So in reality, our seepage problem are mostly associated with this kind of three-dimensional condition, but we need to simplify the complexity in a simple manner. So the field condition sometimes can be idealized kind of one-dimensional or two-dimensional problems, depending on structure shape and surrounding conditions. Total head at this crest of the slope is around 187 feet. The bottom is 1 to 1. So water will flow from here to here based on Bernoulli equations. And then this water flow through the sand seam. So Darcy's law applied in this case. How the water, how fast the water flow through the soils. In this case, sand seam. So this is the very, very simplified version of examples. So later on our tutorial session, I will explain this, and then we can also deal with another examples. Okay, last topic for today. I mean, for these CP's topics, we have um, certain laboratory tests to check soil's permeability, whether it is like 10 to the power of -8, -6, 5 sometimes. How do you know? Yeah, of course, we need to do laboratory tests. So I'm gonna give you a bite-sized video how to test. We have two different tests. We can maintain our water heights, and then we allow them to falling down. So I'll give you two bite-sized videos.
Sample preparation. Weigh the apparatus including the porous disc and reusable steel mesh filter paper. Make sure that all the components are inside the apparatus. Place the soil in 3 layers. Compact it with a hammer. Number of blows will vary according to the desired density. Ensure that the sample achieves uniform density. Again, Take the weight of the apparatus with the prepared soil sample in it. Constant head permeability test. Make sure the top and bottom valves are closed. Connect the pipe with the apparatus. Open both the valves, the soil will start to get saturated. Make sure that the water head remains constant. Allow adequate time for the flow pattern to stabilize. Measure the time it takes to fill a certain volume using a graduated cylinder. Measure the temperature of water. Repeat the process 3 times. Compute the average time, average volume, and average temperature. Measure the vertical distance between the funnel head level and the outflow level. The diameter and length of the soil specimen can be obtained simply by measuring the dimensions. The head difference is also measured. The outflow volumes with different elapsed times have been measured. Therefore, from the volume, length, cross-sectional area, time, and head difference, the permeability can be determined. Thus, the permeability of coarse-grained soil can be determined by constant head method.
This is the different methodologies. Falling heads. Previous one is a constant head. This one is the falling heads.